Okay, let's get back into the lecture slides. We were talking about reaction mechanisms. So we said that, generally when we see a chemical reaction, a chemical equation, we think of that as happening in a single step. But the reality is no, there's a lot of things that are going on at the molecular level, a whole bunch of individual chemical reactions that give us that overall reaction that we're looking at. And we call that basically a reaction mechanism, okay? And again, it's often referred to as a pathway or a mechanism, which basically simply represents all the individual chemical reactions occurring at the molecular scale. Added all up gives us the overall reaction. So those individual reactions are called elementary reactions or elementary steps. So here's an example. So let's consider the reaction then of nitrogen dioxide to form carbon monoxide. The reaction of carbon dioxide and carbon monoxide to form nitric oxide and carbon dioxide. So you might think that that all occurred in one step, but as we seen yesterday, no, it actually occurs in two steps. First, a nitrogen dioxide molecule reacts with another nitrogen dioxide molecule to form a very reactive nitrogen trioxide and a much more stable nitric oxide molecule. So that happened on the molecular scale. This one bumped into this one and formed these new products. Then that nitrogen trioxide that was formed now reacts with a very stable carbon monoxide. And because it's very reactive, it will give up an oxygen to the carbon monoxide to form carbon dioxide, and then leave behind nitrogen dioxide. So these are the elementary steps. These are the things that are actually occurring on the molecular level. To get the overall reaction, all we do is we add up all the individual steps. In this case, there's only two. We're going to cancel anything that's the same, okay, from the reactant side to the product side. So I can see that I have nitrogen dioxide. So there's one there. There's one there, so we're going to cancel out those two. There's no more nitrogen dioxide over here. Nitrogen trioxide, there's one here. Oh, there's one here, so we'll cancel them. Then a carbon monoxide, well, there's no carbon monoxide on this side, so nothing else cancels, so we simply bring down the rest, and there is that overall equation that we were originally talking about, okay? So these are elementary steps. We would say this is step one, step two, and this is the overall equation, okay? Now, you'll notice that NO3 never appeared in the overall equation. We're going to call that a reaction intermediate. These things are highly unstable, and you don't collect a jar of them. They would react with each other, okay? So again, we didn't see it in the overall equation, but it was formed, but then immediately reacted with something else. So a reaction intermediate first appears in the mechanism as a product. This is going to be important because we're also going to find out later on that catalysts don't appear in the overall reaction, but they do appear in the intermediate steps. But a catalyst appears first as a reactant, is where a reaction intermediate appears first as a product. Now, there are exceptions to the catalyst thing, okay? But there aren't exceptions to the reaction intermediate. It always appears first as a product, okay? Okay, now we can classify each one of these molecular events, each one of these elementary reactions, with a term called molecularity. It simply indicates how many particles were involved in that molecular event. For nuclear decay, you don't need any particles. Literally, the molecule by itself falls apart. So there's only one reactant molecule. And we'd call that unimolecular decay. That also happens to molecules when you heat them. A lot of molecules, if you heat them up, they simply fall apart. You didn't need any other particle. That would be unimolecular. We just seen the reaction where the two nitrogen dioxide molecules reacted with one another. Well, that's two particles, and that would have been a bimolecular event, okay? And rare, much rarer, especially in the gas phase. Now, in an aqueous solution, if you have 3 particles coming together all at once, we would call that a termolecular reaction. Now, again, remember, these are only for elementary reactions. These do not talk about overall equations. These are just for elementary reactions. Now, there are higher order molecularity, but in a gas phase, you'd never see 4 particles come together. Maybe in a liquid phase, you'd see 4, but that would be extremely rare. So usually it's molecular or bimolecular, and on occasion, we'll see termolecular reactions. Okay. Okay, so since the chemical reaction may occur in several steps, there's no easily stated relationship between its overall reaction and its rate law. Okay, so this is why we can't use the coefficients in an overall reaction as the orders for the reactants and catalysts in our rate law, because of these individual reactions, these intermediate steps. Now, this is the difference though. For elementary reactions, the coefficients in the balanced elementary reaction, they are the exponents. They are the orders of those reactants and products. Now, we're also going to see that we're now going to take into account both the reactants, catalyst, and products when we're talking about elementary steps. So again, let me repeat. The coefficients in those balanced elementary reactions are going to end up being the orders for the reactants, products, and catalysts. So let's take an example. Let's look at a very simple generic unimolecular reaction. So I got a reactant molecule all by itself, and it goes under some chemistry and becomes products, okay? Or nuclear decay and becomes products. So the rate law is simply going to look like this, right? Because it only depends on the concentration of that single molecule. You could also say, well, this is a coefficient of 1, so it must be a first order. Again, this is only for elementary reactions. Okay? Now, let's say we have a bimolecular reaction where 2 particles have to collide with one another on the molecular scale, an elementary reaction. The rate law would look like this. It would be rate is equal to the equilibrium constant, the rate constant, times the concentration of A raised to the first, times the concentration of B raised to the first. So now we can get rate laws directly from the equations of elementary reactions. If we had 3 particles, a termolecular reaction, in this case, we have 3 different molecules all colliding with one another at the same time, the exact same moment in time. Well, it's going to be rate is equal to the rate constant times the concentration of A to the first, the concentration of B to the first, and the concentration of C to first, since the coefficients are all 1. Well, what if we had this? This again, this is 2 particles, 2 of A. So that at the same time, those 2 A particles are colliding, they collide with B. So again, another termolecular elementary step. So that's 3 particles. This is termolecular. The rate law this time, we could write it like this, right? The rate is equal to the rate constant times the A concentration times the A concentration times the B concentration. We're representing each of the particles that occurred in that termolecular event. But of course, we're not going to write it like this. We're going to write it, rate is equal to A squared times B. Well, notice that that is the coefficients in the balanced chemical equation, 2 for A, 1 for B. So again, for elementary steps, the coefficients represent the exponents or the orders of the reactants and products. Okay. Okay, so in essence, that's all I'm saying. That's all I've been saying this entire time. So now, note that many chemical reactions occur in multiple steps and is therefore impossible to predict the rate law based solely on the coefficients in the overall reaction. So again, you can't use the coefficients in overall reaction to say what the orders are of each of the reactants. Okay. Okay, so let's look at an example. So let's consider the reaction. We have nitrogen dioxide reacting with fluorine to form two nitrosyl fluorides. Okay. The rate law that's been determined experimentally looks like this. So its rate is equal to the rate constant times the nitrogen dioxide raised to the first times the fluorine gas raised to the first. Well, notice that there's no 2 there, right? So if this is the experimental rate law, I know for sure this wasn't a single event. This must have occurred in steps. Now, if this was a 1 and this was a 1 and these both ended up 1s, I still can't say for sure that that was an elementary step. It might be, but I'd have to prove it, okay? But when they don't match up, so this is a 2 and this is a 1, I can say for 100% sure that there has to be at least 2 steps in this pathway, if not more. So again, the reaction's first order with respect to both, and again, the overall reaction, since this is first order and first order, the overall reaction then will be second order. And again, this is what I'm saying. This is all I'm saying, that this implies that the reaction isn't an elementary step by itself. And again, even if this was a 2, that does not prove that this was an elementary step. You would have to prove it experimentally. Okay, so when we have these multi-step reactions, some of these reactions go faster than others, right? So the rate of the overall reaction can only be as fast as the slowest step in the mechanism, in the pathway. Okay, so it's like driving down a single lane road. You're only going to go as fast as the slowest person going down the road. You might have some choice words, some sign language, but no matter what, you're only going as fast as the slowest person driving down the road. Okay, so that's what we call the rate determining step. The slowest of the elementary steps is the rate determining step. So for example, this reaction of the nitrogen dioxide with fluorine to produce 2 nitrosyl fluoride actually has 2 elementary steps. This is a proposed mechanism. It has 2 elementary steps. And so first, the nitrogen dioxide reacts with a fluorine molecule to form 1 nitrosyl fluoride and leaves behind a very reactive atomic fluorine gas atom. Well, that individual fluorine atoms are extremely, individual halide ion atoms are extremely reactive, right? So it then immediately reacts with a another nitrogen dioxide molecule to form a second nitrosyl fluoride. Now, I know that, now I'm not asking you to predict this. Okay, I will always tell you which one is the slow step and the fast step. Okay, but again, when you see an individual atom by itself, especially the ones that form diatomics, you know they're going to react really fast. So I know that this is going to be the fast step and this is going to end up being the slow step. Okay, so now remember, each one of these elementary steps have their own rate laws, right? So for this slow step, the rate law, because this is an elementary step, is just rate is equal to K1 times the concentration of NO raised to the first, because there's the coefficient of 1, times the concentration of fluorine raised to the first. So there it is. There's the rate law for this fast first step, right? This is our, I'm sorry, our slow step, right? So that is the rate law for the slow step. Now there's also a rate law for this fast step too, right? Its rate equals K2 times the concentration of NO to the first times the concentration of F to the first. So it too has its own rate law. But in this case, we don't care about it because it's only the slow step that matters. So if this is the rate law for the slow step, this then must be the rate law for the overall reaction. Now we're going to find out that the rate law for the overall reaction has some qualifiers to it. It must contain either the reactants and or products of the overall reaction. If this rate law contains something that isn't in the overall reaction or the catalyst, right, then it cannot be in the overall rate law. When your first step is your slow step, you don't have to worry about that because it's always just going to be the reactants anyway, and we're always going to see them, either the reactants or the catalyst, and we're always going to see them in the reaction. So we know that both of these exist in the overall reaction. So there it is. That then is going to be the rate law, okay? Now, in a mechanism where the overall slow step is not the first step, it's going to become much, much more complicated, okay? Questions, please ask. Okay, so let's go over this once more. So we're talking about mechanisms with an initial fast step. So when the initial step is slow, it's easy. It's just the rate law is just rate is equal to K times the concentration of each of the reactants raised to whatever power is in that particular chemical reaction. So when the first step is slow, it's really easy to write the rate law for the reaction. The problem is when the slow step is not the first step and contains a reaction intermediate. Remember, it can contain, the rate law can contain reactants, products, or catalyst. The only thing the rate law cannot contain are reaction intermediates. So that's generally an issue when the slow step is not the first step. And so we're going to have to re-express whatever that reaction intermediate is using an equilibrium chemical reaction to get rid of that reaction intermediate out of the rate law. So we gave the example where we had the 2-nitric oxide reacting with the hydrogen to produce gaseous nitrogen and gaseous water. And a proposed, the rate law for this looks like this. Rate is equal, so this was experimentally determined. The rate is equal to K times the concentration of nitric oxide squared times the concentration of hydrogen to the first. So we could see that there's no way that this would be an elementary step. Otherwise, the hydrogen would have been raised to the second power. So a proposed mechanism looked like this. First, the nitric oxides would react with one another to produce dinitrogen dioxide. And this, again, is a very fast equilibrium, which means that as this is reacting to form with a rate constant of K1, N2O2, the N2 is decomposing with a rate constant of K to the -1 back to 2NO, okay? So that's what the equilibrium is. This reaction is going just as fast as the reverse reaction, and so that's our equilibrium. Then this very reactive dinitrogen dioxide reacts with hydrogen, giving up one of its oxygen to form water, and then leaving behind nitrous oxide, N2O. Then again, the nitrous oxide is very reactive and wants to give up its oxygen. And so the nitrous oxide then reacts with hydrogen to, again, produce water and then releases gaseous nitrogen, molecular nitrogen. And so to determine the rate law, well, that's going to be governed by the slow step, okay? So we have two reaction intermediates, right? When we get the overall reaction and we add these up, well, we can see that the N2O2 is canceling, right? And we see that the nitrous oxide is also canceling. So that means that the N2O2 and nitrous oxide are both reaction intermediates. Okay. And so the overall reaction then looks like this, right? We just bring down whatever's left, and that actually gives us the overall chemical reaction that we had seen before. So again, the overall rate law is going to be determined by the slowest step. So that's this guy right here. And you'll always be told what is the slow step and the fast steps and all that. And so the slow step then is going to be rate is equal to K2 times the concentration of N2O2 raised to the first times the concentration of H2 raised to the first. Okay. But again, the problem is that the rate law cannot contain a reaction intermediate, so that shouldn't be there. I'm sorry, I just want to make further changes to this slide. Okay, so everybody gets that, right? So the slow step determined our rate law. The rate law was just the reactants, each raised to the coefficients, and then the equilibrium constant would have just been the K value. I'm sorry, not the equilibrium. The rate constant would have just been the K value for that slow step. So again, there's our rate law, but it contains a reaction intermediate. We got to get rid of that, okay? Can't have reaction intermediates. So since this contains the reaction intermediate, we need to get rid of that. We're going to use the fast equilibrium step to do that, okay? So we got to re-express this rate law and get rid of the N2O2. And we're going to do that by using the first step, which is a fast equilibrium step, okay? So here was our fast equilibrium step. Now notice that we're trying to get rid of the N2O2, and the fast equilibrium step has that. Okay, so we're going to need to first off look at what this equilibrium means. Well, that means we have a rate for the forward reaction. So that means we have rate equals K1 times the concentration of NO raised to the second power. Okay, and as we discussed, K1 and K minus 1 are not equal to one another. They're not the inverse of one another. We're going to find out that that ratio is actually equal to K, the equilibrium constant. We'll discuss that in the next chapter. So here's the rate law for the first forward reaction. Again, K1 and then the NO squared. So we see all that. But then we have the opposite, the reverse reaction. So now this is our products. I'm sorry, this is our reactant going to the products. So this time it's going to be rate is equal to K minus 1 times the concentration of N2O2 raised to the first. At equilibrium, these two things are equal. These two rates equal one another. That's what equilibrium means. Okay, so that means this rate is equal to this rate, which means this expression is equal to this expression. Now, again, remember what we're trying to do. We're trying to get rid of the N2O2. So we're now going to rearrange this equation to solve for N2O2. So we're just going to divide both sides by K minus 1. Okay, so there it is. Now we could substitute this for this. Okay, so that's all I did is I took this and I replaced this with this. Now we have the rate is equal to, this was our rate law. I'm going to take this now and plug it into there. So here's our new rate law. Now this is just our K value. So we could just replace this with just a generic K, and the rate law then would look like this. You can leave it like this if you would like. I want to see this step. I want to see that you went through all these steps. But in the end, we would just write the rate law like this, where this K represents K2 times K1 over K minus 1. Okay, any questions with that? So let's try number 48 from chapter 14. And we have this atomic fluorine, and we write it like this sometimes as a radical. Because remember, atomic fluorine, there's 7 valence electrons on it. And one of them are unpaired. And electrons don't like to be unpaired. So we call this thing a radical. They're extremely reactive. That's why I kept saying the fluorine atom by itself is going to be really reactive. It's going to react fast. So we have the fluorine radical, the fluorine atom, reacting with hydrogen gas to form fluorine chloride and hydrogen. And this thing is This is wrong. This is supposed to be HF. Okay. Okay, so I just want to know what is, so we're assuming that these are all elementary reactions, right? You can only talk about molecularity when you're talking about elementary reactions. So since these are all elementary reactions, what is the molecularity of this reaction here? Taylor, what do you think?
I'm not sure.
Hannah?
Is it bimolec? Oh, are you calling me or somebody
Sure.
else?
Kayla.
Oh, is it bimolecular?
It is, right? There's two particles, so this is bimolecular. It is not dimolecular. It is bimolecular, okay? So it's bimolecular, molecular. Missing an E. There we go, bimolecular. Okay. Caitlin, what would be the molecularity of C, this one here?
Would that also be bimolecular?
Agree, Kaylee? Bimolecular? Eugenie?
No, it's ter.
Okay, you shut yourself off. You muted yourself.
It has 3 molecules.
That's right, right? There's 2 NO and 1 O. That's 3, so it is termolecular. Again, it's not trimolecular, it is termolecular. Okay. Lee, are you there, Leah? Hiding from me. Okay.
Yeah, the lights are just out right now.
D, is this going to be, what is the molecularity of that last reaction?
Unimolecular?
Yeah, there's only a single reactant molecule. You heat it up and it'll decompose into nitrogen gas and water vapor. So this is unimolecular, not mono, but unimolecular. Okay, any questions on assigning molecularity to elementary steps? Everybody good? Okay, let's try number 53 then. Chapter 14. It says tertiary butyl chloride, which has this form. Tertiary means there's 3 of them. So tertiary butyl means there's 3 butyls, okay? And butyl represents 4 carbons. So there's 1 and then 3 carbons, right? So butyl means 4 carbons. Okay, so tertiary butyl chloride reacts in basic solution. So that would be the catalyst. Now these are elementary steps. We'll get to the overall step. Okay, reacts in basic solution to form alcohol tert-butyl, butanol. So this is the tert-butanol, okay? The proposed mechanism for this reaction is 2 steps. We have this first slow step where the tert-butyl chloride reacts to basically ionize to form what this is called a carbocation and chlorine. Okay, the carbocation, which is extremely unstable because carbon doesn't like to form ions, reacts with the hydroxide in the basic solution to form this alcohol, which is our tert-butyl alcohol. Okay. First, it wants to know, what is the overall chemical reaction? How do I determine that? Michael, what do you think? How am I going to determine the overall chemical reaction? What would I need to do?
Break down the bonds, I guess.
I'm sorry? I just didn't hear you.
Can't really hear you.
Okay, I want to know, what is the overall reaction?
Just add them together.
Right. So so when I add them together, what do I do?
Just cancel out on sides, I guess. Like,
Okay, so does anything cancel?
the CH3 3CCl. My bad. Yeah, the one you had your pen on.
Okay,
CH3.
so the cation one. Okay. Does anything else cancel? Nope. So we just bring down the rest. Okay. Does everybody have a hard time hearing me? Could everybody hear me okay? Because this is an issue if you can. I got to do something to change
No,
that.
my internet's just doo-doo.
Okay. No, I know that. That's why I got to come to work. I can't even do this from home, or we would be, half the time would be spent me re-signing on. Okay. Okay, so let's see. What have we got left? So whatever we got left, so we got the tert-butyl chloride. We have the hydroxide. And then we have the chloride. And we have the tert-butyl alcohol. Okay, so there's the overall action, the overall reaction, okay? That's all you do. You cancel out what's similar on both and you get your overall reaction. Okay, are there any reaction intermediates or catalysts in this reaction? Taylor, what do you think?
I think CH3CCl is a catalyst.
This guy here.
Yeah. Because it doesn't show up in the products.
But it shows up here.
Oh,
Remember, a catalyst or reaction intermediate will not show up in the overall equation.
oh, then no. I don't think there's either.
Does this show up in the final overall reaction?
Oh, no.
So that must be either a reaction intermediate or a catalyst. So what is CH3 3C plus? Is it a cat? So what you got to look at, where did it appear first? As a reactant or a product?
Product.
So that makes it a,
Intermediate.
it's a reaction intermediate. And there are no catalysts. The catalyst most likely would have showed up first as a reactant and then disappeared, canceled later on as a product. Okay. I think I said that it was catalyzed in basic solution earlier, which I lied. Okay. It's not. It's part of the chemical reaction. It's not a catalyst. Okay. Okay. Then finally, it wants to know, what is the rate law for this reaction? Where am I going to get the rate law from? Hannah, what do you think?
You can take or find the rate law of the first rate constant. And
So
then
this first reaction?
yeah,
Why?
because it's the slow.
That's right. Rate determining step is our slow step. That's where our rate law comes from. So what is the rate law for that then?
Rate equals K sub 1 times the concentration of CH3,3CCl. But then that's also the overall reaction.
Right. And it's raised to the first because that's a coefficient of 1. And because this does exist as reactants or products or catalyst, okay, so if it's a reactant, product, or catalyst, it's okay. If it's a reaction intermediate, cannot be in the overall rate law. So this not only is the rate law for the elementary step, this ends up being the overall rate law as well. Okay, any questions about that? Okay, let's try another. So this one says, in the upper atmosphere, chlorofluorocarbons, such as CFCl3, absorb sunlight and subsequently fragment.
Could you move the paper down?
Oh, sorry. In the upper atmosphere, chlorofluorocarbons, CFCs, you might have heard that term. Not so much anymore because they kind of banished most CFCs. Hairsprays and deodorants, everything came in frickin' spray cans. And in the spray cans, they'd put these CFCs because they aren't harmful to us. But what they didn't realize is that these CFCs migrated the whole way to the upper atmosphere. And when they reacted with sunlight, they would fragment into chlorine atoms. And we've already discussed that individual atoms of these diatomics like chlorine, fluorine, bromine, hydrogen, nitrogen, oxygen, they're extremely, extremely reactive. So for these chlorofluorocarbons to dissociate into individual atoms in the upper atmosphere was devastating because they'll easily react with ozone. Okay, they'll easily react with ozone and cause the decomposition of the ozone. And what happened is that there's a layer of ozone that basically surrounds the Earth, and it protects us against the UV radiation of the sun. Without the ozone, we will not exist. Plain and simple, we will not exist without ozone. It'll burn everything. I mean, you'll cook. You won't be able to go outside without SPF 100. But the plants can't survive that either. What was happening is that literally they were using so much of this chlorofluorocarbons in spray cans that we were destroying the entire ozone layer. In fact, we caused a absolutely massive hole that still exists today. It's starting to heal. We're doing really good at it, actually. It's starting to really heal. But we were on the verge of wiping out the ozone layer. Okay, so yes, we could definitely affect our environment, and we can take actions to stop that and actually even reverse it. And so what happened? Well, in the upper atmosphere, we have ozone. Now, ozone freely dissociates into oxygen and molecular oxygen and atomic oxygen. Now, atomic oxygen is very reactive, so it immediately wants to react with the oxygen and reform the ozone. So every time an ozone molecule absorbs UV, the way it gets rid of that energy is it splits apart. But then it immediately comes back together, and so we maintain a certain amount of ozone. That's what naturally occurs. That's very fast, and it's an equilibrium process. However, if a chlorine molecule reacts with the ozone, we form this chlorine monoxide and regular oxygen. Well, that chlorine monoxide is very reactive, will react with the oxygen before the O2 can and reform the chlorine, which again is going to destroy the ozone, and then release it simply as O2. Okay? So, again, we want to know what is the overall reaction. Well, we're just going to cancel anything that's similar on both sides. So let's see, we have, so I see no O3s over here, no O3s, Cl, there's a Cl, there's a Cl, there's a ClO, a ClO, there's an O and an O, And so the overall reaction then is what's left. So that's 2 O3 gases and 1, 2, 3 O2 gases. So we go from 2O3 to 3O2. Okay. Any questions with that? Okay, are there any reaction intermediates or catalysts?
There aren't any catalysts, but there are 3 reaction intermediates.
Okay, what are those reaction intermediates?
Oxygen, chloride, and then
Okay,
the
chlorine.
chlorine.
Yeah, and then this chlorine monoxide.
Yeah.
Okay, so these are our reaction intermediates. So again, we have our atomic oxygen, atomic chlorine, and chlorine monoxide. And again, why are they reaction intermediates? Well, you got to see where they appear first. Well, here I can see, okay, the oxygen appears first here and then cancels later on. That's a reaction intermediate. Let's see, the next one, the chlorine appears first here and then goes to there. So is chlorine a reaction intermediate? Is chlorine a reaction intermediate?
Chlorine wouldn't be.
It would actually be a catalyst. Okay. So again, the chlorine appears first as a reactant and then disappears as a product. Now the chlorine monoxide first appears as a product, then is canceled. So it is a reaction intermediate. So this free chlorine, remember, that's coming from the dissociation of this CFC. Okay. So that's actually a catalyst. Can oxygen or chlorine monoxide appear in our overall rate law when we're done? No. What about the free chlorine? Can it appear in our overall rate law when we're done? Yes. Catalysts can appear, but reaction intermediates cannot. Reactants can appear, products can appear, catalysts can appear, but reaction intermediates cannot. As what is the rate law for this predicted reaction? Well, we know that the rate law is dependent on the slow step. So that means it's going to look like this. Rate is equal to K3, right? So K3 times the concentration of the reactants, each raised to the coefficient, which in this case they're both 1, in the elementary step. Okay. By the way, before we get started on this, what is the molecularity of the first step? Kayla, what's the molecularity of the first step?
Is it unimolecular?
It is unimolecular. Keenan, what about the second step?
I'm not sure. I still need to go over that lecture.
Okay, Hannah, what about the second step? What is its molecularity?
Bimolecular.
Say it again.
Bimolecular.
Bimolecular, absolutely. And Michael, what about the third step?
Bimolecular.
Yeah, right. So if we have one particle, it's, you know, basically decomposing. In this case, it's absorbing UV, but we're not going to see that in the balanced chemical equation. So there's only one reactant, so that would be unimolecular. If there's two, that would be bimolecular. And if there was three, it would be termolecular. Now remember, the coefficients count, right? So if there was a coefficient of 2 in front of the O3 and a 1 here, that would be 3 particles, and that would be term molecular. Okay. Okay, now coming back to the predicted rate law. So again, we're going to base it off the slow step, but the problem is that slow step contains reaction intermediates. So we have to get rid of both of these reaction intermediates. Okay, this would be the toughest of this type of problem I could possibly put on the exam, where we have multiple reaction intermediates. Okay, but again, it's really not that bad. So we're looking for an equation that would contain, for example, the oxygen. Well, we can't use this one because that's our rate law. So we're going to have to use an equilibrium step that contains oxygen. And again, remember, that means that we have a forward reaction. So we have the rate equals our K1 times the concentration of O3 to the first. And then for our reverse reaction, we have rate equals, now we're going this way, so it's K minus 1. And then the concentration of our reactant, so O2 to the first and O to the first. Okay. Now remember, these two things are equal because it's equilibrium. So that means that K1 times O3 is equal to K minus 1 times O2 times O. And again, if you have questions, please let me know. Now remember what we're doing. We're trying to get rid of this O right now. So there it is. So I'm going to say that O equals the K1O3. Then I'm going to divide both sides by this here, right? So that would be K minus 1, and that would be O2. And now this is going to go into that, right? So now we have rate equals, so we're going to bring this over. So that's K1 over K minus 1. We already had the K3 here, so I'm just bringing that down. Then we had the CLO. Now we're going to replace this with the O3 over O2. Okay. Everybody still with me? Okay, but we still have another reaction intermediate to get rid of. We see that in this step here, right? There's the CLO there. So again, we're going to do the same thing. The forward rate, that's going to be our K2, right? So K2, and then times the concentration of O3 to the first times the concentration of Cl to the first. And then we have our other rate. And that's the reverse rate. That's going this way, right? That's going this way. So that's going to be K to the minus 2. And then the concentration of ClO to the first and the concentration of O2 to the first. And again, at equilibrium, these two things are equal. So that means that K2 times O3 times Cl is going to be equal to K minus 2, ClO, and O2. And again, we're trying to get rid of this reaction intermediate, so we got to solve for that reaction intermediate. So that means, again, ClO is going to be equal to K2 times our O3 and Cl. Then I'll divide it by this and this, so that's going to be K minus 2 over O2. Now I'm going to take this and substitute it into there. So now I have rate equals our K1, K3 over K1, but I'm going to multiply this to it as well. So that's going to become K1, K2, K3 over K minus 1, K minus 2. Okay. That's a K minus 1 and a K minus 2. And then we have we still have the O3, and there's another O3, right? So that's going to be O3 squared. Then there's a Cl. Then in the denominator, there's an O2, but there's another O2. So that's going to be O2 squared. Any questions with that? Again, all I did is I took and replaced this with this entire thing right here. Now we could rewrite this thing. You could write it as rate is equal to K times the concentration of O3 Cl O2 squared. So is this good? It contains the O3 and O2, but it also contains chlorine. Is that okay that it contains chlorine? So is it okay that it contains chlorine? Eugenie, what do you think?
I am not sure.
Caitlin, what do you think? Is it okay that it contains chlorine?
Yes, because chlorine's a catalyst.
Absolutely, right? We've already established that chlorine is a catalyst, and we know that the overall rate law can contain reactants, products, and catalysts. The only thing they cannot contain are the reaction intermediates. Okay, so we could write it like that, or you could write it as a single line. Rate equals K times O3 squared times chlorine times O2 to the -2. Either one is totally acceptable. What is the overall order of this reaction? Lee, what's the overall order?
2, 5.
I'm sorry?
5.
Pardon
I mean,
me?
oh, I'm sorry, 2.
Pardon me?
2?
What's that?
Wait, I said 5.
Yep. You
And
said
then-
2.
Because then I feel like it was wrong because then you said what
Okay.
and
Let's go through this. What's 2 plus 1?
3.
What's 3 minus 2?
Oh, I did not notice the negative. 3 minus 2 is 1.
Yeah, it's just first order, right? You just have to add these up. So 2 plus 1 is 3, minus 2 is 1. So this thing's actually first order overall.
I'm thinking of the Van Hoff's number, like I,
Yeah,
when you add it regardless. Sorry.
okay. So everybody good then with this type of problem?